Good morning, this is Timmy. Today we are going to talk about the interaction between a line and plane in 3D. Let's start this lesson by visualizing this book and this pen as a plane and a line in 3D. Now, imagine, how can they interact? Let me rotate this. How can they interact? They can either be parallel to each other, parallel and distinct essentially, that means they don't share any point, or they can be parallel and distinct, which means parallel and coincident, which means the line lies on the plane, or they can be not parallel but intersecting each other. Because if a line that is not parallel, it must intersect with a plane. There is no other way. So now let's summarize this discussion on a piece of paper. Lines and planes in 3D, three-dimensioned. They can be parallel, and parallel has two cases: distinct or coincident. Distinct means this is the plane and this is the line. I call this plane pi and I call this line L. They do not share any point. They are distinct, separated. And for coincident, this is the plane, I call it pi again, and this is the line L. The line lies on the plane. And the third case, they can be intersecting, which means not parallel, because a line and a plane that is not parallel, they must intersect each other. Let me draw this plane again. Pi, and this is the line. A line and a plane, if they intersect, they must intersect at a point. Okay. After summarizing, we can actually look at these three cases, whether their systems are consistent or not. What do I mean by consistent? Consistent means they must have at least one solution. What do I mean by one solution? One solution means they must at least share one point. So look at parallel and distinct. Do they share anything? No, of course. Therefore, they are inconsistent because there is no solution. For coincident, the line lies on the plane. Therefore, it is of course consistent because they have infinitely many solutions. All the points of the line are points on the plane as well. So they share a lot of points. They are consistent. And last but not least, intersecting lines. As I said, they must intersect at exactly one point. Therefore, they must share one point. When they must share one point, they are of course consistent because they have one solution. After this geometric discussion, we can now finally solve problems. Look at this problem. In each case, determine if the line and the plane intersect. Once you see this question, you will need to assume they both intersect and you substitute the parametric equation into the scalar equation of the plane, which means like that. X, you substitute. Y, you substitute. And Z, you substitute. And you solve for t. When you solve for t, you can actually get three possibilities. Possibilities of answers. The first possibility, you will get a unique t value, which means the line and the plane essentially really intersect, therefore they yield a unique t value. Second possibility, you will get a true statement. However, this true statement does not give you a unique t value, but it is a true statement. For example, e.g., 0t equals to 0. This is a true statement. However, there is no unique t value. And this case tells you that actually the line and the plane, they are actually parallel and coincident because any point is true. The third possibility, you will get a false statement, such as e.g. 2t sorry 2 equals to 10. This is a false statement because 2 is not equal to 10. And this tells you that both the plane and the line, they do not intersect. So now back to this question, we can solve for it. So we need to multiply them into the bracket. 9 times 5 equals to 45. 9 times 2 equals to 18t plus 13 times negative 5 equals to negative 65. 13 times negative 5t equals to negative 65t. Negative 2 times 2 is equals to 4, negative 4. Negative 2 times 3t will equals to negative 6t equals to 29. Then simplify it. 45 minus 65 minus 4 is equals to negative 24. 18t minus 65t minus 6t will be equals to negative 53t equals to 29. And t will be equals to negative 1. See, for this case, you have a unique t value. That means the plane and the line, they do intersect. And you can actually utilize this t value to find the point of intersection. As I said, if a plane and a line, they intersect, they must intersect at exactly one point. Therefore, there is a point of intersection. So you can substitute this t value back into the parametric equation of the line to find the point of intersection. X equals to 5 plus 2t, which is negative 1. Y equals to negative 5 minus 5t. Z equals to 2 plus 3t equals to 3 equals to 0 and equals to negative 1. Therefore, the point of intersection is coordinate form because point is a coordinate. 3, 0, negative 1. This is the x, y, z coordinate of the point of intersection. Actually, there is another way to determine whether the line and the plane intersect or not. The previous method, which is this method we have just used, this method is actually an algebraic approach. See, we have done a lot of algebra. There is another method which is by looking at their vectors, a geometric approach. You can see, in order to use this geometric approach, I suggest the first thing you do, the strategy, the first thing you do is to visualize by drawing. a plane called pi1 and a line called L1. Let me use another color. From the parametric equation of the line, we know the direction vector of the line M, I call it M, is actually 2, -5, and 3. And from the scalar equation of the plane, you know the normal vector of the plane is actually 9, 13, -2. Okay, now you can see. What I want to say is, if the line is really parallel to the plane, the normal vector of the plane must be perpendicular to the direction vector of the line. There is no other way. And if they are not perpendicular, automatically you know they are not perpendicular to each other, they are vectors. So we can actually use dot product to check for this case whether they are parallel or intersecting. Dot product, you will have two possibilities of answer. First possibility, normal vector dot product direction vector, you'll have 0. If 0 means they are perpendicular, they are orthogonal to each other, therefore this case tells you that the plane and the line, they are parallel. And if dot product of n and m, they are not 0, that means it tells you that the line and the plane, they are not parallel, because the normal vector and the direction vector, they are not perpendicular, they are not orthogonal. Okay, so now we can check for this question. N and m equals to 9, 13, -2, 2, -1, 3. Nine times 2 plus 13 times -5 plus -2 times 3. And you found it is -53, their dot product, which tells you that it is not equals to 0. Therefore, they are not parallel. Which means they intersect at exactly one point. Do you realize what's the difference between these two methods? Obviously, the difference is actually these methods just provide you an answer which tells you that the line and the plane, whether they intersect or not. However, the algebraic approach, other than telling you the line and the plane, they intersect or not, they also tell you the point of intersection. Therefore, you can use these two approaches that suits the question. That's all for today. Thank you. I hope it helps you. Okay, now let's do another question. Similar question, but using the geometric approach one more time. And you see now we have a line and a plane. This is the vector equation of the line. This is the scalar equation of the plane. And now we can do it by visualizing it first. Pi2, and this is L2. The direction vector, normal vector. You know, if the plane is parallel to the line, the normal vector of the plane must be perpendicular or orthogonal to the direction vector of the line. So to check this, we can use dot product. N dot M, the N will be 4, 0, because there is no Y here, and -2, dot, -2, 1, -4. And we can check what's the dot product. And -2 times -4, 0. Therefore, the plane is really parallel to the line. And now, remember, if it is parallel, that means there is two cases. One is parallel and distinct, the other is parallel and coincident. To know this one, you can see their properties. If parallel and distinct, that means they don't share anything. And if parallel and coincident, the points of the whole line will be lie on the plane. Therefore, we can actually use the point of the line and substitute it into the scalar equation of the plane and see whether it is a point on the plane or not. So you can see 4 times 1 minus 2 times 1. See whether it is equals to 11 or not. If it is not equals to 11, that means the point is not on the plane. 4 times 1 minus 2 times 1. It's 2. So 2 is not equals to 11. Therefore, the point is not on the plane. And the point is not on the plane, that means they don't share anything. Therefore, they are parallel and distinct. That's all for today. I hope it helps you. Thank you.